Hello. Here we are with section 6.3 about half-life and doubling time. This is another real-life sort of application of exponential expressions and exponential functions. Half-life and doubling time are a way that things that grow exponentially are described a lot of the time. I don't know if you watched the whole press conference where Donald Trump suggested maybe we can inject disinfectants into our lungs to take care of the coronavirus. Right before that, I forgot his name. The guy was describing the results of some studies where they found that the half-life of coronavirus droplets in the air, if you're in sunlight, is about 1 minute. And this is what got Donald Trump excited about somehow getting tremendous, very bright light inside the body somehow. Like if you can give your lungs a sunburn, maybe that will kill a coronavirus. Well, what he was talking about was the study that said that the half-life of coronavirus droplets, if you're outside and there's sunlight, ultraviolet light, becomes 1 minute. And what that meant was that every time 1 minute goes by, half of the viruses in the air die. And we're going to look at what does that look like with the numbers when you make a table or when you make a formula. And that's what this section's all about. So first up, you got some exercises to do here. So for the first one, you're just filling in a table given this formula for the function. So the formula, a of d equals 1,000 times 2 to the power d over 7, is the result of it is the quantity in grams of algae in a swimming pool d days after the owner stops putting chlorine in it. So if you're not sure what to do, I'll show you the first one real quick. A of 0, we're going to get here, is going to be 100 times 2 to the power 0 over 7. And 0 over 7 is 0. 2 to the power 0 is just 1. Anything to the power 0 is 1. So this gives you 100 times 1, which is just 100. And you're probably going to need a calculator for these. So for example, with this one, 100 times 2 to the power 1/7, that's not something you can do in your head. So you're going to do 100 times 2 to the power 1 over 7. Comes out to be 110.4 grams of algae in the swimming pool after the owner stops, 1 day after the owner stops putting chlorine in it. So I'll give you a moment to pause it here, fill in the rest of the table, try B and C on your own, and then try exercise 2. And in a moment after I give you a chance to do this, to pause it and do it, I'll show you the answers. Okay, so for the rest of these, we're going to need a calculator. We're going to do 100 times 2 to the power 2/7. I'm also just going to hit the second enter button to bring up the previous thing to make it so I can change it quickly. Something interesting happens when you plug in 7, because 7 over 7 is 1. So 2 to the power 1 is just 2. So I don't even need the calculator. I know this is going to come out to be 200, but I'll check it anyways. Okay, so we have 121.9 grams after 2 days, 134.6 grams after 3 days, and 200 grams after 7 days. After 14 days, this is going to become 100 times 2 to the power 14 over 7. And I know that 14 over 7 is 2. So this is going to be 100 times 2 to the power 2, which is 100 times 4. After 21 days, we're going to do 100 times 2 to the power 21 over 7, which is 100 times 2 to the power 3. And to go from 2 to the power 2 to 2 to the power 3, that's just like multiplying by another 2. So this is going to become 800. Alright, so what happens to the algae every time a week passes? Going from here to here, or here to here, or here to here. Every time 1 week passes, the exponent goes up by 1, and the result gets multiplied by 2. So A of D, the amount of algae, doubles every week. Now, this function could be written in this form, because if you have a power to a power, you could multiply the 1/7 times the d. And 1/7 times d is the same as d over 7. So let's see, by what percentage does the algae grow each day? Well, let's figure that out. To get the percentage the algae grows each day, we want to think of this as A of D equals either little a times b to the power d, or if instead of b, you write that as 1 plus r to the power d. That r is the percentage growth rate each day. So this, and that the b is whatever 2 to the 1/7 is. And 2 to the 1/7 is the 7th root of 2, comes out to be 1.104 about. And if you want to write that as 1 plus something, 1 plus 0.104 is the same thing. And that is the r. So we have r equals 0.104. And if you want to write that as a percentage, you could write it as 10.4%. So, to summarize, what's going on here is every time d goes up by 1, the amount of algae gets multiplied by another factor of 2 to the power 1/7, which is about 1.104. So multiplying the amount of algae by 1.104 is the same as increasing it by 10.4%. That's what 6.2 was all about, was a relationship between increasing it by 10.4% and writing this as b equals 1.104 to that power. Okay, so that's the percent growth rate, is 10.4%. Right, so exercise 2 is sort of the same idea, except this time we've got the quantity in grams of some radioactive material in a meteorite y years after it fell from space. So plugging in these numbers here, we're going to get, when you plug in y equals 0, we're going to have 8 times 1/2 to the power 0 over 500, which is just 1/2 to the power 0, which is 1. So whenever you plug in 0, you're just going to get your starting amount, which is 8 grams of radioactive material. Here we're going to have 8 times 1/2 to the power 1 over 500, which is going to require a calculator. It's 0.9986 about. Let's call it 0.99861, just to be a little bit more precise, times 8. Turns out to be 7.9889 grams. All right, after 2 years, we're going to plug in a 2 into this formula. It's going to be 7.9778. Let's call it 7.978. Plug in 3, second entry brings that up, so I can quickly change that 2 to a 3. You get 7.967. Okay, so at first it's decaying extremely slowly, because it's not that radioactive. It's just slightly radioactive. After 500 years, something special is going to happen with the formula. If the y is 500, the formula is going to become 8 times 1/2 to the power 500 over 500, which is 8 times 1/2 to the power 1, which is just 8 times 1/2, which is 4. All right, so then let's see. What happens if we plug in some more multiples of 500? These multiples of 500 are nice because they're going to make it so the fraction gets reduced to just be an integer. So at this point, we can do 8 times 1/2 to the power 1500 over 500. 1500 over 500 is 3. So this is the same as 8 times 1/2 to the power 3. And 1/2 to the power 3 is 1/8. So you get 8 times 1/8 is 1. After 2,000 years, this is going to be 8 times 1/2 to the power 2,000 over 500. 2,000 over 500 is 4. So this just gives you 8 times 1/2 to the power 4, which is 8 times 1/16, which is going to be 1/2, 0.5 grams. Okay, and this, you could have gotten this with a calculator too, but I think it's good to see how the arithmetic works if it's possible to do it by hand. Anyways, what happens to the amount of the radioactive material every time 500 years pass? So here's 500 years passing. It goes from 8 to 4. From this point to this point, 500 years is passing twice. And it went from 4 to 1. From here to here, 500 years is passing once. So here, for this 500 years, it gets cut in half. It goes from 8 grams to 4 grams. Then from here to here, it goes from 1 gram to 0.5 grams. That's getting cut in half. And if 500 years goes by 2 times, it's 4 times 1/2 times another 1/2 is 1. So every time 500 years pass, it gets cut in half. All right. Now, by what percentage does the radioactive material decay each year? So each year, that's when 1 year goes by. So the trick for this one is to write this as 8 times 1/2 to the power 1 over 500, and then that to the power y. And this is an extra hard problem. Maybe I shouldn't have given you this exercise at the beginning because it might have scared you off. Maybe this should have been an example. But anyways, I'll show you the answer here. So the reason I'm doing this is because I want to think of this as a times b to the power y. This 1/2 times 1 over 500 is the b. And we want to know the b because if we want to know the percentage decay each year, that's going to be thinking about what we did in 6.2. That's what the value of r is if we write this in the form a times 1 plus r to the power y. So we got to know what b is, and then once you know what b is, that b is equal to 1 plus r, and then we can figure out the r. So let's see. First of all, this whole thing, 1/2 to the power 1/500th, we definitely need a calculator for. Is 0.99861. So that means every time 1 year goes by, every time y goes up by 1, the amount of radioactive material gets multiplied by 0.99861. And if, or in other words, there is 99.861% remaining. So if you have 99.861% remaining, how much are you losing? You're losing less than 1%. Let's figure out what that is, because this is 1 plus r. That's the r we're trying to find. So to solve this for r, you just subtract 1 from both sides. 0.99861 minus 1 is about negative 0.1385. Let's call this negative 0.139 if you round it a little bit. And that as a percentage, if you move the decimal place over 2 times, we can say r is negative 0.139%. So, in other words, to summarize everything that's happening here, every time y goes up by 1, every time 1 year goes by, you multiply by 1/2 to this power, which is the same thing as 0.99861. So every time 1 year goes by, you have 99.861% of the previous year's radioactive material. So the amount that you lost was 0.139%. That's what's going on here. All right, so I'm going to go over what's in the next box in the next video, because I think people are more, this is important, and it's more likely that people are watching the beginning of the video because maybe you just checked your answers here and you skipped the end. That's okay. Anyways, let's go over the main concept of this section next.